Nice. And then,
Is it that one that's in space?
I already turned on.
Okay. We should turn on one more, I think, because this is still the only part of the game.
Oh, okay. It's the one.
Ah. There. Like this? I think this is good.
Yeah.
Oh, I have it, don't worry.
Honestly, I think I just.
Okay.
I mean,
Because like I'll try to get here by 3, but some really won't, and then just don't want any panic when we can't get the stuff working. QT just went. Can I pull this a little more, or is that it? Can I pull this? And you want Beyonce? Or you want the website? The website. Graphics, yeah. Oh, and then you want the
I feel more comfortable.
if you want this on your laptop.
I probably need less time staring at the computer screen.
We should, because when you connect the so let's make sure. Okay, be sure you don't press escape. Although I have to. This is a PDF, so.
oh, this is
Yeah,
the.
this is a PDF. Yeah. And then.
Is it?
Yeah.
Yeah, it's BGA. So.
1, 2, 3.
Is it on?
Yeah.
Oh, there we go. And then screen is over here. Oh, actually, you're using a PDF. What's your expectation for this one? Wait, let me just double check. Fine. Can we also just try it on? Since we don't see like wait, think which one? Yeah, I don't know. I don't know. Oh, okay.
Yeah, I think that one was just the same.
National University. Oh, cool. And then how do you escape? Okay. Okay. And then if it doesn't work, just right over it. What is someone asked? What is that error?
We'll see.
Let's say.
Kitty could give it.
Okay, that great. Use Russian. hours tonight. See if anyone comes tonight. Because I'm thinking Thursday night should be on Thursday night because I was excused on Friday.
Oh, is it?
Yeah. And but they might come Thursday. And then I'll probably have one. Yeah, I'll see if anyone wants to tonight. And then maybe tomorrow. I'll just ask. So we were thinking about office hours. If we were to have office hours, would you come? Because that's an important question when we are trying to figure out when to do office hours. Like, if no one's gonna come, then it's gonna be really awkward for us. So, would you actually come?
Is there
In the evening? It's in the evening.
Avery's will be in the evening, mine are Thursday morning.
I will go.
Okay. Alright.
See,
Awesome.
Wait, when were they again?
So I'm thinking about doing because Thursday night I'm thinking no one actually wants to do Thursday night. The 106B assignment is due on Friday, and when's 106 actually? Wednesday.
At 5 p.m.
Okay, so maybe
4 p.m. this week, actually.
what did you say?
I said 4 p.m. this week.
4 p.m. this weekend.
All right. Let's. Okay, yeah, because that's something at Thursday night. Okay. I'll have our office hours tonight. I'll figure out what time, and then probably
I think 106B isn't due till Monday, right?
it's not.
Oh,
That's what it says online. It says due Monday, October 14th.
Oh, okay.
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 Morning.
All right. I'll have office hours tonight for sure, and let me update on Thursday night. Thursday morning, I will have office hours.
Thursday morning I will have office hours. But
And then-
Avery's are
So I'll have office hours tonight. I'm gonna make a post on Piazza soon. It'll be tonight sometime around like 5 to 7 or something. Alright, it'll be pretty chill. I'll just be sitting there doing my own thing unless someone comes up. Okay, and don't forget, even if you haven't started working on the assignment, feel free to come. You don't have to have any questions ready. You can just come and you can sit there and work. And if you have questions, I'll get there to answer. Okay.
That's good.
Yeah. Another thing is, if you have any questions about any of the material that we covered, I know we've covered a lot in the last 2 weeks. Feel free to also comment. Okay. And as office hours are Thursday morning, 9 to 11. 11 a.m. Okay. And then remember, you can always post on Piazza. Okay. We're fine with private posts. If you have code in them, that's fine. Just make sure they're private, so we will be able to reply.
And we'll be doing like a quick overview of the Sunday morning lecture today, so you guys will feel the
Tonight I'll probably do them something in my old unit. Yeah. What I usually do. Okay, so I know one of my section E's, my old section E's is here, but if you've ever taken my section, I do office hours as I hold them in old unit and I buy them possibilistics. Let's see. Were you there for that?
No, I wasn't there.
You were? Okay. Well, you missed a lot.
Can imagine.
Yeah. So we have an old unit. So because specifically the assignments are due these 2 weeks, so we'll have more office hours these 2 weeks. Yeah. I'll have office hours today from like 5 to 7 or to as late as people come, and then Anna will have office hours Thursday 9 to 11. Yeah. If there's some other times you want to meet, let us know and we'll figure out.
These are more just like scheduled weeks and times, but we're pretty flexible. Mine are going to be, right now, for now they're going to be on the Tressiter's second floor patio facing Dinklage Auditorium, which is very long, but it's very worth it. It's a great view. But that might change if people can't really find it.
I'll just say I refer to myself in third. Or anytime. For those of you in 106B, is the auditorium still overflowing?
No, a lot less people showing us.
Okay, like how full is the auditorium? 50%?
Yeah.
Half empty? Okay. We're doing, well, actually they're over enrolled, so we're doing slightly better. Yeah. we're doing slightly better in terms of coming. Alright. Yes, yeah. It'll be somewhere around like tab. Because that won't
Alright, we'll get started. So as you may recall from last lecture, you guys, Avery said that this lecture is the most important lecture to attend, so you guys are already doing a great job. But it's true, today we have some really exciting themes to teach you, so we're going to get started and hopefully try and make our way through all the material. So first, if you guys remember, we asked you about any bad dad jokes in the survey, so you'll be hearing some of the highlights from your peers. And if you are the person that wrote it, feel free to announce yourself, otherwise I'm just giving credit to my But, all right, so for today, we're going to quickly recap one of the things we didn't finish from last time, container adapters. Then we have a couple announcements to make, and then we're going to dive into associative containers and iterators, which are going to be basically the most fundamental concept you'll learn in this class, pretty much above anything else. All right, so for a brief recap, if you guys recall from last Thursday, so week 2, we covered sequence containers. In the standard C++ library, there are 5 types of sequence containers. Vectors and decks are the 2 types that we looked at on Thursday. There's also list, array, and forward list. Still useful. I would definitely recommend looking them up online at CPP reference if you're interested in looking into them, but we will cover them. So as a reminder, the main big difference between the Stanford vector and the standard vector is the difference between the .at and the bracket functions. So remember just that the .at throws an exception when you access an index that's out of bounds versus the bracket notation causes undefined behavior. And you'll also remember last time that there was actually a problem with the example. It was like, oh wait, I said that it wouldn't work, but somehow it still worked. In fact, little did we all know this, but that was actually that was actually the exact intended behavior. So it turns out that when you try and access an out of bounds index using the bracket notation, it actually causes undefined C++ behavior. And this term undefined behavior is something that you'll see throughout a lot of C++ documentation. And basically what it means is that something has gone really, really wrong. And the reason that is because the behavior isn't actually predictable. For example, on a Windows machine like mine, it could be that after you've called vec I on an out-of-bounds index, your program will just no longer run, but also not tell you that something was wrong. Or it could be that on a Mac, for example, it'll continue running as though nothing went wrong. Which is to say that you just can't predict it, which is why this is a big difference to keep in mind. The other part that we covered was a deck, and just as a brief review, a deck is everything a vector can do, but with the added ability that you can add an element to the front of the basically array very, very quickly. But with the trade-off that it is slower to access middle elements. So again, if you go back to the idea that you both want to learn the tools you have and learn when to use each, now you guys know the trade-off between a deck and a vector, so you know which ones to use for which applications. Okay, so, yep, one more time with our favorite thinker statue, vector by default, deck if you're mainly a thinker. All right, does anyone have any questions from last lecture before we go on? Yes?
So, I know the Stanford libraries have something called stack. So is the stack sort of equivalent to the deck?
Say that one more time.
Like, where does the stack fit into this?
Yeah, the stack. Okay, so it's almost like I planted you again because that's actually exactly what we're covering next. So great question. Anyone else have any other questions before we move on about sequence containers? Perfect. All right, so thank you. That's a great question. So you guys may have recalled from one of Superior X that you guys learned about something called stacks and queues. So it turns out the standard C++ library has those as well, just wrapped in this unfamiliar name called a container adapter. And we'll see why it's called that in a moment. Okay, so as a brief review, you guys should have all just recently learned this, but in case it's been a little while, stacks, you have two main functionalities. You can either push an element onto the stack at the top, or you can pop it off the top again. So last in is the first element out. On the other hand, queues, you can add, there's a PDF thing up at the bottom. You can add an element to the back of the queue, or you can pop out to the front of the queue, just like any line that you see at the store. So I have a question for you guys, actually. Given what you know about the vector and deck, in C++, in standard C++, again, nothing simultaneously, nothing is magic and everything feels magical. But how do you think that C++ may have implemented stacks and queues under the hood? Does anyone have any ideas? So yeah, all the way in the back.
So just a deck with limited functionality?
Say that one more time.
A deck with limited functionality?
Yeah, that's an awesome guess. So as it turns out, C++ stacks and queues are really just vectors and decks under the hood, but with limited functionality. So if you were to look at the specs online, what it looks like, we'll actually see on the next slide. But just to confirm, a stack is really just a vector or a deck, but that only allows the pushback and popback functions that we saw. And a deck is just, and a queue is really just a deck that only allows you to push things to the back of the deck and take things out from the front of the deck. And then additionally, stacks and queues both ensure that you can only access the very top element of stacks and queues. So yes, Brian.
So if they're actually implemented as like vectors, are they actually like much faster? Because I thought we were told like because of the limited functionality they were much faster, but if they're actually vectors under the hood,
Great question. So the question is, since they're actually just vectors and decks under the hood, aren't they basically the same speed or efficiency as a vector or deck? I will answer that on the next slide. So yeah, good job. We're continuing Avery's pattern of predicting what comes next. But really quickly, you guys can see this for yourself. So again, one of the things we want to teach you in this class is how to read the C++ documentation. So if you go to the stack or queue C++ documentation, you can see in a tiny font there on your laptop later on, it says that stacks and queues are really just building on vectors and decks. And so it's for that reason, actually, that they're called container adapters. They're not actually containers in themselves. They're actually just adapting the vector and deck containers to suit this particular need. So I think that's a great question. That's the question I had is, so in that case, why use a stack or deck at all when you have a stack or queue at all when you have a vector or deck? To answer that, once again, we're going back to our favorite design philosophies of C++, one of which is we want to express ideas and intent directly in our code. So when we have something that's like a line at Starbucks, where we know that the only functionality that we need is to add someone to the end of the line or take someone from the front of the line, we want to express that intent directly in our code. And so that's why such common use cases like a queue or a stack eventually got their own type called a container adapter, where there are types that we can use directly. The other style, of course, being that we want to show our developers that we don't actually need any of the other functionality of vectors or decks, we only need these particular functionality. And then to answer Brian's question, which one is more efficient? As it turns out, because we are guaranteeing that the only things you can use on a stack or queue are the pushback, pushback, popback, and pop front functions, those functions are actually all, if this doesn't make sense to you, it's okay, but they're all actually constant time functions, which means that they are, in fact, faster than a vector in a deck just because they are only using the fastest functions on a vector or deck. So a vector or deck has the same efficiency for those particular functions, but stacks or queues ensure that you are only using those fast functions. Yeah.
I'll really add something, which is the first philosophy you see over there, give the programmer full control. If you go back to the previous slide, one more slide. Yeah. If you look at the documentation, you'll actually see up there, like under that template thing. Oh yeah, it's this box that you see over here, the red box, this one. Were you gonna talk about this? The red box. Okay. Yeah. So suppose you were writing your own program and you didn't like the fact that the stack of the queue used a deck, right? Suppose you were like, okay, I'd rather the stack use some other data structure. Then you're actually allowed to pass in, like you can actually, when you create your stack, you can say, don't use a deck, use this other data structure. So if you like a vector instead of a deck, you can, when you declare your stack, you can say stack, bracket, t, comma, vector. That's the second parameter you see over there, the container. Yeah, by default, the default value it gives is the deck, but you can actually give it any container you want. Okay? Yeah. One thing about C++ is like these classes, they try to hide what's underneath them. So if you don't want to think about them, you can just use a stack as you would expect it. But if you care about like just eking out the last bit of performance, you can customize, you can create your own special data structure to use as the stack, essentially.
Yeah, that's a great point. Yeah, so before we move on, does anyone have questions about, yeah?
If you used your own custom data structure, would you have to define your own like op and queue methods?
Yeah, great question. So the question is basically how would you use your own defined data structure? So as it turns out, C++ has, or in this case in particular, there are particular requirements that your custom data structure would have to fulfill. In this case, they would have to fulfill the requirements of the type called sequence container. So as long as you fulfill those requirements, and in this case, it is the pushback and popback functionality for stack, for example, then you can use your own class. But yes, you would have to define them for yours. Yeah, that's a great question. Any other questions about stacks or queues? Awesome. Okay, so so far we've actually covered two large parts of the standard library, sequence containers and container adapters. So there's actually one other type of container called associative containers that are, again, also a type that you may be familiar with from 106B or X. In fact, that you may have just learned, I believe, last Friday if you are in the class right now. So, again, associative containers are a type of container that have no idea of a sequence. There's no way that you can access them by an index 0, 1, 2, 3, 4. Instead, the data is stored as a set of key value pairs. In the C++ standard library, there's 4 types of associative containers. Maps and sets you may already be familiar with. There's also 2 things called an unordered map and unordered set, which we won't get into today, but we'll briefly explain what they are, so if you are interested, you can go on and look them up yourselves. So from 106B or X, you may have learned what a map or a set is. So can someone quickly tell me actually what is a map? What is the definition of a map? Yeah, go ahead.
So it's basically just a data structure that allows you to store sets of 2 different types of data, and so you define what 2 types of data those sets are composed of, and then when you call the map and you pass the key, so like the first type of data, it will retrieve the associated second piece of data.
Exactly, perfect. And that's exactly why they're called associative containers. You're associating one key type of data with one value type of data. Exactly. And one other question for you guys is, can there be more than one key of the same exact value in a mapper set? Who thinks yes? Who thinks no? All right, great, perfect. Yeah, so you guys are already pretty familiar. So some differences between the maps and sets that you already know and the C++ version, or and the standard C++ versions. So one thing is to know that under the hood, maps and sets do sort their elements based on some ordering property of their keys. They're not necessarily stored in an array like we're familiar with vectors, but they are stored sorted. Which means that, say, going back to the idea that Avery brought up of defining your own classes, if you wanted to create a map, say, of student, of a class called student, then you would somehow need to define your own less than operator to be able to know how to compare students so that the map could keep them in sorted order. So that's something that we'll cover more when we talk about classes, but something to keep in mind. So again, going back to the idea of you have to define certain operations on your classes to be able to use them with things like maps or sets. So unordered maps and unordered sets are exactly like maps and sets functionality-wise, except they don't store things sorted under the hood, which means also that if you're trying to iterate across a map or set, you can't guarantee that it'll pop out, say, in alphabetical order. So these are some details on how unordered maps and sets work. Again, the big takeaway is that if we are defining our own classes, as we'll do later in the quarter, we'll need to define specific things in order to be able to use these data types. But for now, we won't delve too much into the unordered ones. One other thing that we want to bring up is the idea of, again, when do you want to use each? So it turns out regular maps and sets, keys in sorted order, and you can, they're very fast at iterating through ranges of elements because they are sorted, whereas unordered maps or sets, they're faster to access individual elements by key. So again, we won't go into it, but that's the use case in case you guys are building things of your own and want to know which sort of data type to use. And I saw 2 questions back there. Yeah.
Yeah, so you mentioned that we needed to define our own less than operator.
Yes.
Is that the only requirement for using our own custom classes, or is it other operator that we need to define?
Yeah, that's a great question. So I'd have to take a look again to see if there's another one besides less than operator. I believe for maps and sets, the less than operator, and additionally some things like being able to, I believe actually for maps and sets that is the only requirement, but I would have to look that up too. Yeah.
Yeah, so that's also a concept that we'll discuss next week, which is like what kind of, like each class has a special property, like okay, do they have a less than operator? Do they have some specific property that lets you put them into maps and sets? We'll discuss that next week when we go attendance. Yeah, because I think maps and sets also require like copyable elements, something
Yeah,
like
that's
that.
true. Yeah.
Does the standard C++ set also follow like set theory principles, which is overload all of the operators? Or
It does not, but next week we'll talk about algorithms, where there are generic algorithms which do.
To recreate those exact functionalities. Yeah, any other questions? Yeah.
Is the C array a type of sequence container?
Yes. So sequence container tends to describe things in the STD in the standard library, whereas the C array is a part of C and actually not a part of the STL. But it is essentially a sequence container.
Okay. Are vectors built on arrays?
That's a great question. So that has to do with, that can actually differ by implementation methods. So that's actually one tricky thing that, that isn't really clear when we talk about C++. C++ is actually just a language, and different organizations can choose to implement the C++ language in different ways. That said, most people tend to use a bunch of standard implementations. For example, if you've heard of GCC, that's one very common standard implementation. So it depends on the implementation, but an array is the most common one. Yeah.
CS106B or X covers like implementation of data structures, like in 2 weeks I think. So we won't cover that, but it is a good thing to explore.
Yeah, good questions. Any other questions about sets or maps? Yeah, one more.
So for unordered maps, what makes the lookup time constant? Like, why is it so fast compared to regular maps?
Great question. So this is actually a question that you'll also explore in other classes. So the question was, why is it that lookup in maps is so much faster than other data structures, which is something you might have learned in 106B or X. So you'll actually get to explore that in classes like CS161 algorithms.
Last week in 106B, sometimes we'll cover it.
And sometimes the last week of 106B covers it. But to give you guys a sneak peek, really how maps and sets are implemented is using something called a binary search tree, if you've heard of that. So you'll learn a lot more about those, but those are basically designed to have relatively quick like search and access times. But you will definitely learn more about that. And feel free to ask us more about that after class. Yeah.
That's like 106B week 7.
Gotcha. Yeah. Yeah.
Sorry, just something I thought that sets like there were actually like a mathematical set like unordered. So what do you mean by like he's in sorted order instead?
Yeah, so this actually gets to the one of the fundamental ideas about sets of maps. So we teach them to you as compared to a vector, they are not in sort of like a sequence of where you can say like index 0 contains this element 1, 2, 3. And we teach it to you as like sets of maps or like clouds basically, where it's just like everything is like somewhere in the set. But you'll notice that if you've ever tried to print out things from the set, that they always come back in sorted order. For example, if you've learned something called a for each loop, and you do something like for elements in set, print out that element, you'll notice that they always come back in sorted order. And that's because we can't access the elements by some index like 0, 1, 2, or 3, but they are still kept in sorted order under the hood. So it's not in sort of like a linear sequence of buckets, but it is sorted. So that's like, yeah, that's a weird distinction that mixed me up a bit when I first learned. Great question. Okay, awesome. If we have further questions, we will continue to ask at the end of the lecture. But for a quick example of what C++ maps look like, part of the reason we wanted to show this example is because it's actually relevant to your assignment as well, assignment 1. So what we've done here is we've implemented a function called getLine, which asks the user to type in a response. And that function is similar to something that you'll want to do for your assignment. If you've read the assignment spec, under the advice, tips, and tricks, it'll say something like, reference the getLine in lecture. That's the getLine that we're talking about. And then for this program, what we want to do, most of the program's been written already. We just want to point out, again, some examples of maps being used in practice. So once again, just like with any other object, this is how you declare a map without initializing it. And then some of the other functionality that we want to point out. So how you access the value of a map, you may have seen from 106B or X, is that you do something like frequency map and then the key, and then to set it, you would say something like A. Or to access it, you would do something like, you would do something like int A equals frequency map.word. So one big difference that we want to emphasize is that, oh my gosh, just like with vectors, there's a difference between using the frequency map .get function versus the frequency map bracket word function. So in the Stanford library, both of those do the same thing, I'm pretty sure. But in the C++, in the standard library, the .get function will do, what it'll do is it'll search the map to see if the key already exists, and if it doesn't exist, then it'll throw an error. Whereas in the bracket notation, it'll check if it exists, and if it doesn't exist, it'll automatically create an entry and default initialize it. Does that make sense to people, the difference between the bracket and the get notation? Okay, awesome. And then the one last thing that we want to emphasize here is that, so you can go back and read this code. It's posted online to the website, but that's the one big difference that we want to emphasize. Yeah, Monique?
So what's the best way to check if a key in a map ends? Since if you just like look at the bracket notation, it creates it for you, and if you do the docket, it gets an error. So do you check for an error, or what's the best way to do that?
Yeah, that's a great question. So whether you use the .get function or the bracket notation depends on your functionality. If you want it to automatically create an entry if it's not there already, then feel free to use the bracket notation. If you want to check whether it's in there before you add it, then that's actually the exact next thing that we're going to cover. So that's a great question. So if you wanted to, how could you check whether an element is already in the set? You might remember from the Stanford library that there's something called like map.containsKey, and that's what you can use to check whether the map already contains a key. We're going to teach you actually how the Stanford library implements that. And it turns out there's a couple different ways. The first of them being what you see down here. So maps come with a function called count that counts the number of times that something appears in your map or set. So can someone tell me what are the possible values for count to return on a map or set? So once again, it's counting how many times a key appears in a set.
Zero.
You got it. Awesome job. Yeah. So it seems kind of weird. Why would you have a function that can only actually return 0 or 1? It turns out C++ does actually have data structures where you can have multiple keys of the same value pointing to different values. So that's why this count function exists. But exactly as you said, for maps or sets and unordered maps or unordered sets, count will always return 0 or 1. So in this case, we're using it as an implicit Boolean to say if it exists, if it returns 1, then we know that it exists in the function. Otherwise, then it does not exist. Does that make sense to people? Any questions?
I'll just add a super unimportant side note. If you don't like the function count, I think C++ 20 is releasing a function called contains key. Yeah.
Are they actually?
Yeah.
Okay,
So
that's
if you don't like the name of this function count, since it doesn't make sense why it's returning well, you think it returned an int, but actually you use it as a boolean. Then I think in C++ 20 that they contain key.
Is using implicit boolean like you're actually just doing it equals equals and like putting 0 or 1? Because that would happen naturally. Right?
That's a great question. So the question was, is using the implicit Boolean faster than manually checking whether it equals 1? My guess is actually that a compiler that's set with a high optimization level would actually make those the same anyways. But in this case, using the 1 as an implicit Boolean is just like a very common stylistic construct. So feel free to use it. In the end, it most likely won't make a difference in your program. Yeah, great question. Yes?
And when you use the bracket notation,
Yes.
and like the keys, if the key is not found, it's added, and what is the value that it's set to? Is it 0?
Yeah, great question. So when you're using the bracket notation and it's not found and automatically adds it, it default initializes whatever the value type is. So for an integer, it'll automatically set the value to 0. Yeah, good question. All right, so this was just executing the program, and again, you guys can go on the website and the code is there so you guys can play around with it. But just to show some of the functionalities. Yeah, any other questions? Awesome. Okay, so yeah, just to recap some key takeaways. Again, that should be get, not add. Get versus the bracket notation, and then how to tell whether it contains a key. We saw count. In C++ 20, there's going to be a contains key. There's actually one other method of determining whether or not an element is in a map or set, and we'll actually learn that next lecture using iterators, which is the concept that we're learning later today. So you'll get to see a bunch of different ways to implement contains key. And then set, we didn't see that in action, but it works very similar to a map. In fact, you can really think of a set as a map where there's an implicit value of either true or false. True if it's in the set or false if it's not. So if you're ever wondering like what sorts of functions works on sets versus maps, pretty much every function that works on a map works on a set except for the .get and the bracket notation because there's no such thing as a value in a set. So some handy tricks for you guys. But and then we also posted some code if you want to look at how sets work, but we'll just leave those online if you guys want to play around with those later. Cool. Any questions about anything that we've covered so far before we dive into the next section? All right. Yeah, one question.
So with iterators, is that faster than just using .count, or what's more efficient?
Yeah, we will actually talk about that question about which method of checking whether a key is in a map or set, which method is more efficient. We'll talk about that when we cover it. Yeah, that's a great question. Cool, so we are doing great on time, you guys. So we have a couple of announcements for you to take a quick break from C++. So, first is assignment 1 has been released. It is due the Thursday after this Thursday. But remember that you also have 3 late days to work with, 2 of which you can use on any of the assignments. Remember also that you have to complete 2 of the 3 assignments, and the first 2 tend to be a lot shorter than the third one, so if that weighs in at all. That said, the third one is really fun to do, so up to you guys. Avery and I are having office hours. My office hours will be Thursdays from 9 to 11 a.m. On the Truster's second floor patio. facing Dinkelspiel, and please feel free to message on Piazza if you don't know where that is. It's a great study spot.
Yeah.
And
And
Avery.
slight modification, probably for this week only. I'll have office hours. I think I've said Tuesday, today, 5:30 to 7:30 at inside Old Union. Although if you don't see me, I'm probably at Tap waiting for food. And then I'll be there Wednesday. What time did I say it was? Sometime. I said something on the Piazza Post. Double check the Piazza Post for when on Wednesday.
Yeah, so the slides are a little out of date. The Piazza has our final office hours times. Cool. So one other thing we actually wanna tell you guys is that applying applications for section leading are now open. So Avery, if you wanted to give the spiel.
Oh, sure, yeah. So every quarter, the CS 198 program reaches out to current 106B and X students, as well as those who finished CS 106B and X, and to see if there are any interested applicants. Now, the fact that you're all sitting in CS 106L, interested in learning C++, I'm sure all of you would make great section leaders to teach the introductory CS 106 classes. Now, essentially what the process entails is there's an application online, you apply online, and then the 198 coordinators will contact you for more information on how the interview process goes. If you are selected into this amazing, wonderful community, then it's a 2-quarter commitment to section lead for the CS 106 classes. All right?
Yeah, and feel free to talk to me or Avery after class about it. It's been a really awesome community. It's actually how we found out about this job, CS 106L lecturing. And then you'll get a lot of cool opportunities to like talk to professors, meet industry people at like special events, things like that. So definitely recommend. Yes.
So it sounds like being a TA?
Yeah, so if you are in 106, or if you happen in 106A, B, or X, your section leader, that's exactly what it is. That's exactly what you'd be doing, is teaching a section of your own.
Yeah, we have a little weird thing about terminology. TA technically refers to, is it Catherine? Catherine Rubin? Yeah. It refers, the head TA, yeah. So, so you might hear some people use it interchangeably. This job is for to be a 106 section.
Yeah. Yes, go.
Do late days work the same way as in CS 106B, where it's like one late day is the next class
Great
rather
question.
than an actual day?
So the question is like, do the late days, are they 24 hours or are they the next class day? So because we're on Tuesday, Thursday, and it's sort of weird to have, I guess, a late day from Thursday to Tuesday, because it's super long versus Tuesday to Thursday, we decided that it would be 24 hours. That said, we are like, this is a 1-unit class, we are very flexible in terms of like late deadlines. So if you have an issue, like talk to us first, and we can always work something out. But yes, late days are 24 hours, and you have 3 late days. Yeah, and actually that's a great lead-in. So one other thing we're gonna be releasing tonight is a feedback form, because we wanna hear from you guys, what are the ways that we can improve? For example, is our pace slow, fast? What are things that you'd like to learn? Things like that. So following tradition, if you fill out the feedback form, you can also get another late day. So again, we are here to work with you guys, but we'd love to hear what you guys are thinking of the class and any feedback you have.
Yes. And those who are watching on video, please also fill this out as well.
Yes, shout out to video.
Yeah. The only one comment that you should not put is poor video quality. Alright, but anything else, please comment, but we really want to hear from you. This class is also, we are flexible with our content as well, so we do really want to hear what you want to learn and what you think about the class so far.
Exactly. Awesome. Yeah, any other questions? If not, then, okay, so assignment 1 was released this past weekend, so something we really quickly wanted to do was to give you guys an idea of what exactly it is you're building. So you may have seen this online already, but if you go to the assignment page on the 106L website, you should see that it links, if you click on assignments, it links to a live web demo. And so this is ever so slightly different from the thing you guys will be building because this is implemented in the web, whereas yours is going to be in C++. But this is essentially the output of what you guys are programming. So to give an idea, we can click through, I'm gonna decrease that a little. So you can see something like 3 grid, starts out as some random permutation of dots, and then eventually makes its way into a beautiful graph visualization. So if you haven't read the assignment handout already, definitely go do that, but you can also find this online and play around with it, and you can get an idea of what your final program should eventually do. And this is also just a motivation for you guys to see like how cool it is that the thing that you're building with just super simple standard C++ tools is going to be. One other thing that we want to mention is that, and then it's also kind of fun to just go down the list and see how everything works. But one other thing we want to mention is that the assignment spec looks pretty long. It's something like 14 pages, I believe. The actual assignment itself is not that long, we promise you. It's actually, the amount of lines of code that you're going to write shouldn't be too long, so if you're having any sort of difficulty or like something about the spec isn't clear, definitely reach out to us. Like we're here to help answer questions, things like that. Yeah, any questions? Well, actually before I do that, a couple things that I wanted to highlight from the spec in case they're useful. So at the bottom of the homework assignment, there's something called advice, tips, and tricks. They mentioned that there's a suggested loop structure that you should use in chapter 3 of the course reader. And I think some people might be like, there's a course reader? So the purpose of this announcement is partially to announce, actually, yeah, we have a course reader. This course reader was written by Keith Schwartz, if you've taken a class by him. You can find it on the website in the top right corner under course reader. The class doesn't actually follow that course reader exactly, but it's a good reference. So that's what we mean by course reader. And then we just saw getLine in our maths exam today. So that's what we mean with in the homework. The last thing is that in general for style advice, again in this class, we aren't emphasizing style as much as the regular 106 series. That said, just for yourself as coders, there are just a lot of good habits for yourself to get used to. One of those is like decomposition, like breaking up your program into smaller, easy to read parts. And then, for example, using constants in this assignment where there's a lot of random numbers like pi. Yeah, so if you guys have any questions about those, definitely let us know. Yes?
Can we use Stanford libraries to finish this assignment?
Great question. Can we use Stanford libraries to finish this assignment? And the answer is no. So that's a great question. That might be what you're used to. But the purpose of this assignment is actually just to create a really nice, easy way for you to get your hands dirty in programming with real industry standard C++. So again, Stanford C++ libraries will not be out in the real world once we leave Stanford, sadly. They're really useful for learning concepts, but part of this is to not challenge you so much with concepts, but really challenge you with just getting the syntax under your hands. So yeah, so we definitely want you to use standard C++. If you have any questions about like how to get started, ask us. Definitely ask us. Yeah, great question.
I'll just add on to that, which is in the last 4 lectures, we've learned enough to actually be able to implement almost, well, most of the Stanford library functions, especially the ones regarding like file I/O and all sorts of stuff. During lectures 2 and 3, we implemented get integer, if you remember that. So that might be helpful for your assignment. And the example code online also shows you more examples, like how would you implement something like prompt user for file. All right. So I don't recommend just copy pasting the lecture code. Make sure you understand the code and be able to write something similar in your assignments. Right.
Awesome. Yeah. Another question.
The PowerPoints from past lectures on Piazza?
PowerPoints are all on the cs106l.stanford.edu website. Yeah, if you click on the lectures tab. Yeah, great question. Yeah.
Should constants like pi be global?
Yeah, that's a great question. Should constants like pi be global? In this case, because our thing is only, it's a single file, we're not interacting with multiple classes, feel free to make them global. And if you're confused on what global means, come talk to us. I'm not sure whether CS106B and X will cover that.
No. So you can make them as global constants.
Yeah.
So if you declare const static.
Yeah, and we can actually, if we have time, I'll run a quick example of like the global constant at the end of lecture. But yeah, that's a great question.
We'll talk about namespaces a few weeks from now.
Awesome. Okay, so before we dive in, I want to say that, again, this next part is really the fundamental building block of C++. So get excited because it is very, very cool. So one more time, this is where we are right now in class. So we are covering the standard template library. So far, you guys have learned basically everything there is to know about containers and container adapters. So you've already learned 2 parts of this 5-part sequence in the STL. You'll notice that both containers and adapters are pointing to iterators, which is to say that both of them use something called an iterator, and we'll get into that in a moment. But so yes, we are gradually making our way through this term. Okay, iterators. How many of you guys have heard of something called an iterator before? Quick show of hands. Okay. Oh, okay. So that's a pretty decent amount then. So you guys may have already had your mind blown, but we will continue to blow it today. So one motivating question for why something called iterators. Well, one question you might have noticed when we were talking about associative containers is that we can't iterate them just using a normal for loop like we would have with a vector or a def, saying something like for in I equals 0 up to the length I plus plus. And again, that's because we can imagine maps and sets as like a cloud of data, not necessarily ordered in a very nice linear way. So the question is, how do we iterate over a map or set? First, this is a cute note taken from our previous lecture, Ali. With iterators and from now on, we're really delving into what makes C++ special, which is how generalizable it is. So just to emphasize, we are going on a journey. We could, in theory, fly to the very end destination and just tell you guys what iterators are, but then we would miss the experience and we would also miss out on 3 best-selling books. So instead, we're going to just like take it slowly. So even though you guys may have heard about iterators already, we just want to emphasize exactly how they're used and why we use them. Okay. All right, so iterators. Iterators are something in the Stanford C++ library that allow iteration over any container. So all of the sequence and associative containers that you guys just learned, iterators can be used on them, whether they are ordered or not. So to get a mental model of how iterators work, for those of you who haven't seen them yet, let's say we have a set that looks like this. It's a collection of 1, 2, 3, 4. Iterators are a device that let us view this non-linear container in a linear manner. So it allows us to treat this cloud as though it were sort of a nice sequence vector-like object. How are they able to do this? We don't actually care for the purposes of this class, but it goes back to Manuka's question about how are maps and sets implemented under the hood, which is like traverses of binary trees. If you're interested, feel free to ask us again after class. So to get a mental model of how to use iterators, there are a couple common functions on iterators that you guys will be using for basically all of the functions that you'll be learning from this class onward. One of them is the .begin function, which returns an iterator. There's an issue with the PowerPoint, but it returns an iterator that points to the very first element in the collection. How do you store it in a variable? So that actually brings us to a question of what is the type of an iterator if we wanted to store it in a variable. On the one hand, so if you actually, one nice feature of Qt Creator is that if you start typing functions into Qt Creator, it'll actually automatically suggest functions for you to use. And in this case, you can see that it suggests a function called begin that has a type iterator begin. And so actually, the type of an iterator is literally an iterator. And the iterator depends on the type of the collection that you're using. So in this case, it's a set of integers iterator. So easy to remember. And then one other common function that you guys are going to be using is the dereference. So in this case, dereferencing this pointer means that you're going to output the value 1, which is what it's pointing at. The third common function that you guys are going to use is the ++, which increments an iterator, and so on. So again, dereferencing to read the value, incrementing to move the iterator, and so on. And then the last common thing that we do with iterators is to check whether we've hit the end of a collection by reading in myset.end and comparing that to our current iterator. So that was a really brief intro into the 4 common functions of iterators, but to give you an idea of how iterators work. I saw a question back there. Yeah, go for it.
The dereference operator is not actually a pointer, right? It's just,
Yeah. Oh, that's a great question. So something you may have seen is that from a class such as 107 or 110 is that there are these things called pointers that you can also dereference to get a value. I believe that iterators may be implemented as pointers under the hood.
For vectors, yes.
Yes.
Yeah, for vectors, iterators are just pure pointers.
Yeah, so for sequential containers, iterators really are pointers under the hood. I'll have to look them up for associative containers.
No, because the B++ has to do something different.
Got you. Is dereference the same though? We will look that up and get it back to you. But yeah, there are some small differences to make this iterator function universal.
Two questions. One, what? Can you explain what the dereference operator is again? Or
Yeah, great question. Okay, so we went through that really quickly. So for those of you who haven't seen this before, so the dereference operator is just this piece of syntax where you place it in front of the iterator essentially to tell the iterator, I don't want the arrow itself, I want the value that the arrow is pointing to.
okay.
Yeah, so that is what the dereference operator is. Great question.
And why do you do plus plus at the beginning and not at the end in this case?
Yeah, so as in why is the plus plus on the left side as opposed to the right side? So this is something called a prefix versus postfix operator. So something you may have seen in classes is something like in for loops you see I++ a lot versus plus I. In this case they do the exact same thing. The one difference between having pluses at the beginning versus at the end of the iterator is just at what point do you execute the plus plus. It's a really minor detail, but it's actually useful for your 106B or X exam, so I'll actually say it in class. The plus plus means that you first increment the iterator before using it, versus when the plus plus is on the right side, it means you use the iterator and then increment it. So in this case, using the iterator means just retrieving the value, so it doesn't matter what side you do it on. Yeah, good question though. Any other questions? Yes.
Do the iterators work on sets and maps?
Say that one more time.
Do the iterators work on sets and maps?
Great question. Do iterators work on sets and maps? In fact, that's one of the motivating reasons why iterators were invented. So absolutely, and we'll see that again in the next couple of slides. Yeah. Question back there.
So if you have like a container that has a continuous memory of the vectors,
Yes.
is like indexing or using like a for each loop faster than the iterator?
Yeah, so the question is indexing directly into a vector faster than dereferencing an iterator?
Yeah, or looping over using iterators.
Or, sorry, say that one more time.
Looping using
Or
iterators.
looping through an iterator. I see, so using like the for loop versus using the iterator. So I believe, let me think about how they'd be implemented.
I think it's similar.
I believe they'd be basically the same because when you're doing a for loop across a vector, really what you're doing is, in fact, I believe C++ may actually under the hood be using an iterator to implement that. So for example, when you're doing things like a for each loop, like for element in vector, it is actually implementing this exact iterator loop underneath under the hood. For arrays, it may be slightly different, but in terms of speed, it should be almost identical, if not identical.
I just want to also mention that the standard libraries, they do use iterators. It's just we don't show you the iterators.
Yeah.
But if you actually look at the standard implementations, they use iterators all over the place.
Yeah, right.
So iterator itself is the memory address for the box, right?
You can think about it like that. Yeah, it's slightly different from a pointer in ways that we'll have to get back to you, but you can basically think about it like that.
Now, the key idea is iterators are like a sort of abstraction where
Exactly.
you're not actually worrying about like what exactly how it's implemented. You just know that it's pointing to some element, and you can say next or previous on that iterator to get like some next element.
All right. So in the last minute, what we want to do. So again, the four things that you usually use iterators for: creating, dereferencing, advancing using the plus plus, and then comparing against the end when you finished. So in the last minute, what I'm going to do is show you some common iterator functions. All right, so the main one being this while loop. So we can actually You can actually see here, basically, there's two ways of using iterators to loop over containers. And you can see right here that we're using them for sets, so partially answering your question. But if we were to write it again, one more time, what we want to do is creating the set of int iterator equals the container.begin to retrieve an iterator pointing to the beginning of that container. We would dereference it to print out a value right here, and then we increment it to move it along to the next element in our imaginary linear vector, set string of elements. And then finally, we can tell that we finished looping over the container by comparing it to whether our current iterator is equal to the end iterator. The other common structure that you guys will see is using the for loop, so doing exactly the same as the while loop, but just wrapping it in a for loop version. So we wanted to put this up there just so you guys have it for reference, and then feel free to run this at home. With that, I'll ask, does anyone have any questions about iterators in our last minute? Yeah, right there.
So, is the advantage of using an iterator over a for loop essentially that you don't have to figure out what the start and end of the for loop is? Is that basically the only advantage?
Yeah, that's a great question. So what are the advantages of iterators? So we were really just going into the functionality of like how do you use an iterator, but we haven't actually told you like why they're cool or why C++ implemented them. So actually let me do that in the last couple minutes. I wasn't sure whether to say for next lecture. So why are iterators powerful? A lot of scenarios require us looking at some sort of container without actually knowing what type of the container it is. And what iterators allow us to do is it allows us to abstract away what the container is. And I'll show you more what I mean by that in a minute. So again, the key idea is that it allows us to go through any container of elements in a standardized way. So this is the example. So let's say we had a vector of integers and we wanted to count the number of recurrences of some particular value. So you can imagine that we would write a program that looks like this. Can we make this work for another data structure like list? Yes, we can, and in fact, the way that we do that when we're using iterators is to replace the type of iterator. And we can do the same. Let's say we wanted to use a set instead of a list. We do the same. And you can see, really, that the key thing here is that nothing at all about the logic of our program changed except for the data structure. So that's a foreshadowing into what we'll talk more about on Thursday, which is iterators allowing us to standardize functions across any type of iterator set. So that is the one key takeaway. Iterators can be used across any container.
And then next week we'll get to templates. That's where we'll generalize it all.
So